Hey folks, this is Captain Jones here talking to you about something called recursion. Today we're going to define that, and then our objectives are to be able to identify a recursive function and describe the base case, and then explain how a stack is needed to support this concept. So let's get started. Okay, so a recursive function is a function that's been defined in terms of itself. So the first example given from the book is that for factorial, by way kind of demonstrating that this function is defined in terms of itself, the book kind of uses this hexagon here to indicate, this is the function factorial, and when we call that function, we might need to call itself again. So we have sort of a nested hexagon here inside the factorial function. Here's how that function might get written in Python, where ultimately we're trying to compute the value of n times the factorial of n minus 1. So this involves a function calling itself. This would sort of go on forever unless the function itself had something called a base case. So this is, you can see it here, kind of, as soon as n equals 1, then we'll return this value, which also happens to be the way that factorial is defined. A factorial of 1 is 1, and anything higher than that is itself times the factorial of 1 less. So if we try to do this in LC3 assembly, we might code this factorial subroutine to do stuff, and when we need to call ourselves, we would do just like we did before. We're gonna save the registers that needed saving, and then call this function and try to call factorial. And the problem with this is that if for R1 and this value memory save R7, as soon as we call our function a second time, they're overwritten. So the initial values that got saved in these two locations are totally destroyed on any subsequent call to this subroutine. So this doesn't work for what should be sort of an unlimited number of recursive function calls. In order for a function to be able to call itself, we need some sort of generic data structure that can kind of expand to store these values, not in hard-coded dedicated memory spots, but can expand to store as many of those values as we need to make as many recursive function calls as we want, and then to sort of collapse back down as we finish our that list of function calls. And that perfectly describes the stack. So, in order to turn our factorial function into an actual subroutine call, what we need to do is modify just slightly, so that instead of saving these values here in dedicated memory locations, we are pushing them onto a stack and then popping them off a stack when we're finished. And I'm realizing now I'm missing something from my notes that I'll get added a little later, which is that to just point out that the reason why we're pushing so many values is because since the function can call itself, in these couple of steps right before we make our subroutine call, we have to save both the caller register R7, because this function is calling another function, and also the callee registers, because when this function is the one being called, it has to save those registers as well. So R1 and R0 end up being callee saved registers. R7 is the caller received register, and we have to do both because the factorial subroutine is both the caller and the callee. I know it's a bit of a mind meld, but if you're struggling to hang on to this point, stick with me, and I recommend reading the textbook also to kind of help solidify the recursion. And here we're using the push and pop as mnemonics for pushing and popping register values onto and off of the stack in order to save those registers instead of specific cases in memory, which would get overwritten if we tried to do that. So the last thing that should be mentioned about recursive functions is that logically, every recursive function can be implemented in some iterative fashion, meaning using a loop of some kind. So here's an example of defining the factorial function using a for loop instead of using a recursive function call. And so this is one of the reasons why the book says factorial is sort of a bad example of recursion, because Um, the iterative solutions are typically faster than the recursive function calls because we don't need to keep kind of pushing and popping items off of the stack. And in this case, the iterative solution is also at least as simple as the recursive function call. So factorial is not necessarily something that you would write in a recursive style. But the book does give a great example of a problem that would be very difficult to resolve in an iterative fashion, which is this example of the maze solver. It's totally possible to write this as not an iterative function, not as a recursive function, but as an iterative function. But it would be much more difficult. So certain problems kind of lend themselves a little more nicely to factorial solutions. To recursive solutions than do iterative solutions. Okay, so that was a quick one. All we're doing is taking a look at what recursion is and to show you some examples, at least one of what a recursive function looks like. We wanted to identify that every recursive function requires a base case. You can see one here. Otherwise, it just ends up sort of calling itself infinitely and never stopping. And on the LC3, the only way that these recursive functions work is by using a data structure that lets us kind of expand as needed to store our caller and callee saved registers, as many of them as we want, and to be able to reclaim those as the stack kind of collapses back down. Without the stack, these values in memory would get overridden on anything more than one recursive function call. All right, folks, that's all I got. See you next time.